Hi, my name is Angus Cameron, leader of the BYU Mars Rover Team. Over the past 7 months, we've worked hard to create a next-generation Mars Rover.
Last year, a drive motor failure caused our rover to tumble down a steep slope. This year, the mechanical team has made several design changes in order to fix these issues. First, we've machined a new frame for the rover. The frame features a modified rocker bogie design and can traverse very rough terrain. We have also added 6 brand new drive motors with increased torque output and integrated feedback control. This will allow us to estimate position and trajectory on a new rover for the autonomous terrain traversal task.
The robotic arm has been completely redesigned and is now lighter, stronger, and more precise than last year's design. Carbon fiber rods provide the structure, while linear actuators give us high torque and a large range of motion. All of our motors and actuators have integrated feedback, which allows us to do both forward and inverse kinematics in multiple frames of reference. Our end effector uses differential gearing to achieve high torque and precise control. The compliant hand allows us to grip a variety of objects and perform various tasks.
Our autonomy and navigation team is excited for this new autonomous terrain traversal task. We begin with 2 GPS points and generate a path of waypoints from start to end. As it goes through this path, it will use data from the GPS and IMU to estimate its states using extended Kalman filter. As it detects obstacles, it can dynamically replan and move around those obstacles and then return to the original path so that it avoids any unsafe terrain or any large drops or just sudden rises that it can't take. Once we get within a certain radius of the gate, we'll detect the tennis ball and it'll command wheel velocities in order to turn the rover to face the gate. It'll have an estimate of how far away it is from the gate and it'll advance far enough forward to finish the task.
This year, the electronics team is dedicated to providing and building a robust and modular system that's much more reliable than previous years. To meet this goal, we have been converting much of the wiring into PCBs. This change is allowing us to have a much cleaner layout and fewer connections, which will result in better performance and faster component replaceability. The Jetson works hand in hand with a PSOC microcontroller to interface with below the motor drivers for our linear actuators and the science module on the arm. This powerful processor allows us to perform many onboard calculations, thus reducing the amount of information that we have to send from the rover to the base station.
Our communication system allows the rover to transmit images from all critical angles of the rover back to the base station. We will also be receiving 3D data from a Z stereo vision camera and a RealSense LiDAR system. The communication system has already undergone rigorous testing in various environments. It uses a dual polarity omnidirectional antenna to optimize our coverage over the target area. So far this year we have already tested it and it has been able to transmit at a distance of 1 kilometer away.
Our main objectives with the science module are twofold: efficient mechanical design and precision analysis of scientific data. The mechanical design will allow the driver to perform all required tasks and procedures without needing to move the rover a single inch. Carefully calibrated actuators control a tool rack with moisture, conductivity, and temperature sensors. We also have the capability to collect 2 separate soil samples with an auger. With this cutting-edge design, we've enlisted the help of student experts to select dig sites and interpret data.
We've been trained to understand geologic structures and stratigraphy, which, in tandem with powerful optics, will help us to select scientifically relevant dig sites. Visual analysis will allow us to review macro and micro soil structures preserved in the geologic record of the area. Observations such as preserved river channels, soft sedimentary deformations, smectitic textures, and pyroclastic tuffs are direct evidence of liquid water and possibly life.
Our system is tailored to collect samples at a specified depth, preserve soil structure, and allow the sample to remain contamination-free as it's transported back to the lab for further analysis. Once in the lab, we will complete detailed lab analysis, including X-ray fluorescence, magnetic susceptibility meter, a pH probe, and a variety of biologic tests looking for specific elements required for life.
We are on schedule to complete our rover before June. We've been testing the rover weekly, and we are confident that it will be a top performer at this year's competition.